Hello everyone. In the previous video, we had learned the basic concepts of partial differentiation. In this video, let us learn how to differentiate a multivariable function using the method of partial differentiation. Okay, this is the first problem. Evaluate dou z by dou x, dou z by dou y, dou z by dou u if z is equal to x cube plus 2x squared y plus y cube plus 2y squared u plus u cube. You can observe that z is a function of three different variables, independent variables, that is x, y and u. I'm asked to find all the three derivatives of z with respect to x, y and u. Now let me start differentiating with respect to the first independent variable. Differentiate z with respect to x, I'll say. So obviously y and u to be treated as constant. So differentiating z with respect to x, I get differentiation of x cube is 3x square. Differentiation of 2x squared y. 2y is a constant. Differentiation of x squared is 2x. So I get 4xy. Differentiation of y cube is 0. Differentiation of 2y squared u is 0. Differentiation of y cube is 0. All these three terms, the differentiation becomes 0 because none of the terms are there. None of the x terms are there in this particular terms. So therefore, on simplification, you get dou z by dou x as 3x square plus 4xy. Similarly, differentiate z partially with respect to y. Now you have to treat the variables x and y, x and u as constants. So when you differentiate, you get differentiation of x cube will be 0. Differentiation of 2x squared is a constant. Differentiation of y is 1. Differentiation of y cube is 3y squared. Differentiation of 2y squared u will be 2u is a constant. Differentiation of y squared will be 2y. And differentiation of u cube is 0. So simplify this. It is 2x squared plus 3y squared plus 4yu. Then differentiate z partially with respect to u now. Therefore, differentiation of x cube is 0, 2x squared y is 0, y cube is 0. Differentiation of 2y squared into u. You have to differentiate u, that is equal to 1, and differentiation of u cube is 3x squared. So therefore, on simplification, you get 2y squared plus 3u squared. So these are the three first order partial derivatives of z with respect to x, y and u. We'll see the next problem. Second one. Evaluate dou z by dou x, dou z by dou y if u is equal to x power y plus y power x. So you can observe that u is a function of x and y. So they have asked us to find the partial derivative of u with respect to x and y. Now first of all, let us say differentiate u partially with respect to x. So I'll keep y as a constant. I'll treat y as a constant. So what happens? Differentiation of x power y. The differentiation of x power y is of the form x power n. So we know that differentiation of x power n is nothing but n into x power n minus 1. Therefore, differentiation of x power y becomes y into x to the power y minus 1. Then differentiation of y power x. Now this is nothing but of the form a constant raised to the power of the variable. Therefore differentiation of a power x, you know that it is a power x log a. Therefore differentiation of y power x becomes y power x log y. Okay, so this will be the partial differentiation of u with respect to x. Now moving further, I have derivative of u with respect to y. So I'll say differentiate u partially with respect to y. So first term becomes of the form constant raised to the uh, power of variable. Therefore, differentiation of a power x is a power x log a. Therefore, differentiation of x power y becomes x power y into log x. Then differentiation of y power x is nothing but x into y power x minus 1. So these two are the derivatives of u with respect to x and y. Next, find the first and second order partial derivatives of z, which is equal to x cube plus y cube minus 3axy. You can observe here z is a function of x and y. So I get two first order partial derivatives and four second order partial derivatives. Now first of all, first find the first order derivatives. For that I'll say differentiate equation 1 partially with respect to x. So you get dou z by dou x, which is differentiation of x cube is 3x square. Differentiation of y cube is 0. Differentiation of minus 3axy is minus 3ay. So this is the first order partial derivative of z with respect to x. I'll call this as equation 2. Now you differentiate equation 1 partially with respect to y. Therefore, differentiate dou z by dou y will be equal to differentiation of x cube is 0, differentiation of y cube is 3y squared minus 3ax. Differentiation of y becomes 1. So the derivative becomes 3y square minus 3ax. I'll call this as equation 3. Now equation 2 and equation 3 is giving me first order derivative of z with respect to x and y respectively. Now let us find the second order partial derivative. The second order partial derivative, if I want with respect to x, then I have to differentiate equation 2 again with respect to x, that is. Therefore, differentiate equation 2 partially with respect to x again. So that gives me differentiation of the RHS will be differentiation of 3x square is nothing but 6x, and differentiation of 3ay will be 0 because none of the x terms are present here. Therefore, you get the first and the second order derivative, that is zxx will be equal to 6x. Now, moving further, now let us differentiate equation 3 partially with respect to x. Now, it is dou by dou x of dou z by dou y. Dou z by dou y is nothing but 3y square minus 3ax. So this to be differentiated with respect to x. Therefore, differentiation of first term becomes 0. Differentiation of second term will be minus 3a. Therefore, we get zxy as minus 3a. Now, differentiate equation 2 partially with respect to y to get zyx. Therefore, dou by dou y of dou z by dou x is nothing but 3x square minus 3ay. When I differentiate this, the first term becomes 0. The second term is nothing but minus 3a. So therefore I get zyx equal to minus 3a. As per our previous discussion, you have observed that zxy is same as zyx. Now, moving further, we find dou square z by dou y squared, that is obtained by differentiating equation 3 partially with respect to y. Therefore, dou by dou y of dou z by dou y, that is nothing but differentiation of dou z by dou y with respect to y. So when I differentiate this with respect to y, I get the first term as 6y, second term y term is not there, therefore this is 0. So zyy will be equal to 6y. So this is the partial derivative, second order partial derivative of z with respect to y. So all the four second order derivatives are found, among which we have seen that zxy is same as zyx. Now, moving on to the next problem. If v is equal to x square plus y square plus z square raised to the power minus half, then prove that dou square v by dou x squared plus dou square v by dou y squared plus dou square v by dou z square equal to 0. Now I have to differentiate v partially twice with respect to x, y and z and show that the sum is equal to 0. So I'll first of all write the given function v and now differentiate v partially with respect to x. So it is of the form x raised to the power of n. Therefore, it is n into x to the power n minus 1. Then it will be minus half into x power plus y square plus z square raised to the power minus half minus 1, which will be minus 3 by 2. Now differentiation of the base function, differentiation of x square will be 2x, y square and z square is equal to 0. Now here 2 and 2 gets cancelled. Therefore you get minus x into x square plus y square plus z square raised to the power minus 3 by 2. This is the first order derivative that you get. Now, if I differentiate equation 1 again with respect to x, then I get dou square v by dou x squared. Then here it will be the product rule, because in dou v by dou x I had x into the function, so it's the product of two functions. So apply product rule and differentiate. So it is first function into the differentiation of the second plus second function into differentiation of the first. When I simplify, it will be minus of x square plus y square plus z square raised to the power minus 3 by 2. And here you observe that the term 2 gets cancelled and you get 3 into x is x squared. So it is x square plus y square plus z square raised to the power minus 5 by 2. Now from these two terms, this is the first term and this is the second term. From these two terms, I am taking minus x square plus y square plus z square raised to the power minus 5 by 2 as a common factor, because here minus 3 by 2 is there. So you can clearly write that as 5 by 2 plus 1. So if I have any function f of x raised to the power this power, I can clearly write it as f raised to the power minus 5 by 2 into the function f raised to the power of 1. So that is how I have taken raised to the power 5 by 2 common outside. The remaining in the first term is x square plus y square plus z square, and the term remaining in the second is minus 3x squared. Now you simplify this. Minus 3x squared plus x squared will be plus 2x squared minus y squared minus z squared, because we have multiplied this minus sign inside. So this is the simplified form of dou square v by dou x squared, and I'll call this as equation 2. Similarly, I can find dou square v by dou y squared and dou square v by dou z square in the similar pattern, and this is what is being named as equation 3 and equation 4. Now the LHS that we require is dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. So I'll be adding all the three equations, that is equation 2 plus equation 3 plus equation 4 gives me the RHS. So these terms, x square plus y square plus z square raised to the power 5 by 2, I can take common outside. The remaining, when I take the sum, that gives me 0. So 0 into any term will give me finally equal to 0. And that is how we have proved dou square v by dou x square plus dou square v by dou y squared plus dou square v by dou z square is equal to 0. This equation is known as the Laplace equation in 3 dimensions. So we'll just note these points which will be helpful in solving any kind of problems. So first of all, we have dou square v by dou x square plus dou square v by dou y square equal to 0. Then this is the Laplace equation in 2 dimensions, and it has a wide applications in the field theory. And this is the equation which we have seen now, and this is the equation, Laplace equation in 3 dimensions. So any function v which satisfies the Laplace equation, that is known as the harmonic function. Any function v which is satisfying the Laplace equation is known as the harmonic function. Now observe the equation, partial differential equation, dou square u by dou t squared equal to c square dou square u by dou x squared. This partial differential equation is known as one-dimensional wave equation. Similarly, if I can generalize the equation, and if the same equation can be written either in 2 or 3 dimensions. So we have written the wave equation in terms of 3 dimensions as well. Now the solution, z is equal to f of x plus ct plus phi of x minus ct is the solution for the wave equation, which is particularly known as D'Alembert solution for wave equation. Now also observe the equation dou u by dou t equal to c square dou square u by dou x square. This partial differential equation is known as one-dimensional heat equation. Similarly, I can write the heat equation in terms of 2 and 3 dimension. The 3-dimensional heat equation is given by this equation, and the constant C what we have in the equation is actually known as a dissipation coefficient. So these were the few important partial differential equation, that is heat equation, wave equation and the Laplace equation. So these were the 3 major partial differential equations that we have come across, and we have also studied in this video the method of solving the multivariable function and how to differentiate these multivariable functions using partial differentiation. Now in the next video we'll be studying about the total derivatives. Thank you.